Hello, in this video I'm going to say a little about mounts for telescopes. So, this could be a tripod or some other contraption that's holding your telescope up, along with the way that that is then connected to the telescope, the main body of the telescope, usually a tube that you've got that's holding the lenses or the mirrors of the telescope. So before we get on to the different varieties of them, of which there are lots, and I won't be able to go through all of them, but I'll cover the main types. Why is this so important? Well, mounts are often overlooked by people when they first get into astronomy because they don't seem that interesting compared to the telescope itself. But your observing sessions are a lot more enjoyable and a lot more productive if you've got a solid mount. And we want something which is going to move smoothly. It's not going to be jumping around when you're moving it about. When you're actually moving the telescope around the sky, pointing it at different objects. So we want that movement to be smooth. We want something which is going to be, if you're an amateur astronomer, transportable. We can't always have a dome set up in our back garden or go off to some fancy observatory. So you've got that factor. You want it to be solid. You want it to be damped. So you don't, solid as in it's not jiggering around all the time. Because when you're looking through the eyepiece, you don't want the thing that you're looking at to be continually jumping around every time you brush against the mount of the telescope. You want it to be solid. And if you do get any jiggling around because someone's walked into your tripod, then you want it to damp down pretty quickly. If you don't have all of these things, smooth motion, solid mounting, and damped mounting, then as I say, you're enjoyment of your observing session is going to be much reduced. So you very quickly come to the view that the mount for your telescope is as important as the telescope itself in a lot of cases. So that's why it's worth talking about them. As I say, they come in a wide range of different styles. You can classify them, I suppose, in two broad camps. We've got the Altazimuth ones, which I'm going to look at on this slide, and then the Equatorial mounts, which I've got on a subsequent slide. So these Altazimuth ones, you could write that out with a hyphen in if you wanted. So you got, because it's two parts to the word really. We're talking about altitude and azimuth. So these are the two directions that we're moving a telescope through. So this second picture here is probably the best one to be looking at the moment. This looks a bit like a cannon, doesn't it? And okay, I know how this is going to be moving around. You're going to be able to move the telescope up and down. The end of the telescope is going to go up and down like you would with the end of a cannon, and you'll be able to swing it around in a compass direction, a sort of bearing. So moving up and down, that's the out bit, that's the altitude going up and down, and then swinging it around, that's your azimuth. Now, these are intuitive to use because you've just got this straight up, down, and side to side. This is pretty easy. If someone says, well, point the telescope at the moon, well, you just look at where the moon is, and no one would have any trouble in just swinging the telescope around and pointing it straight at it. They're very intuitive. So that is an advantage of them. They're also cheap to, comparatively so, they're cheap to manufacture. So that is good. I mean, you can see this one, this second picture here, it looks quite cheap to manufacture, doesn't it? When you look at the materials, okay, it's not to say it's going to be easy to put it all together, but it doesn't look that high tech compared to other designs that you might have seen on telescopes, particularly when we get onto the equatorial mounts. And that's great, particularly in this case. This is an example of a Dobsonian mount. So this is named after John Dobson, who was the guy who, he didn't really invent the mount, but he popularized it in the 1960s. And these sort of telescopes, so remember we're making a distinction between the telescope and the mount here. So the mount is a Dobsonian mount. The telescope is going to be a Newtonian reflector in this case. You can see that. You can see the secondary mirror here. Actually, it's hard to tell on this. It might have a correcting mirror at the front. It's really hard to tell in this picture, but this could be open here with the exception for the secondary mirror. So you're going to have a big mirror at the bottom down there. The light's going to come in, hit the mirror at the bottom. That's going to reflect it back up. This is going to be a parabolic or a spherical mirror going on there. It's going to reflect it back to the secondary mirror. It's going to come back up the tube, and then it's going to come out to the side of the eyepiece here, which is where the observer is going to be looking in. So we've got to make that distinction between the mount, so the Dobsonian bit down here, and then the Newtonian reflector. But these sort of telescopes, which often just get described as being Dobsonians, I mean, these are the ones that people sometimes call light buckets, because if you want to get into deep sky observing, looking at galaxies, nebulae, things like that, so these faint objects, you need to capture a lot of light. So you want a large aperture telescope. So aperture, remember, is the diameter of the opening there. So you want this to be as big as possible. Essentially, you want as big a tube here, a width of tube at least, as possible on the telescope. So that means you want a certain type of mount which is going to be able to support it and not be crazily expensive, because you're trying to engineer some precision bit of metal work which is going to be able to hold this up on a more conventional mount. So that's what makes Dobsonian mounts really appealing, because they're cheap, they're easy to use, and they can support these really big telescopes. I mean, you can see in this second picture here, we got a variation of it, because all that matters from the telescope point of view is that we've got the primary mirror down here, and we've got a secondary mirror supported up the top. What's going on in between? You don't necessarily need a solid tube there. That's fine. You don't need that. I mean, in a very dark sky, particularly if you haven't got the moon around, I mean, you can leave these things open and just have these tubes. You can then dismantle the tubes, and then you're breaking it down into something you can put in the back of a car, easily transport around, and then just reconstruct it. You know, if you're wanting to block out a bit more light pollution that might be getting in around the sides, you can just wrap it in a bin bag or some other dark material around there. And then again, we've got something which is easier to use and transport around and is more practical. So you get different designs on these, but you've still got the Dobsonian setup. You've still got this mount at the bottom, where you've more or less just got a support for your primary mirror. I mean, here you can see they've put it on wheels as well to make it even easier to move it around. So again, these are both Altazimuth approaches. You don't have to have everything like this. I mean, this fourth picture here, this is a fork mount, you know, for obvious reasons. You've got, you know, a base there, which in this case is going onto a tripod. But then you've got a fork. You've got these two arms, which are then holding the telescope in between. But you can see this is the same axes of rotation that we had on the Dobsonian. So again, you can move the telescope up and down in altitude, and you can swing it around in azimuth. So this is working in the same way as these Dobsonian mounts. So why wouldn't people use these all the time? Well, you do have a problem with them when it comes to tracking objects. So if you think about looking at a star in the sky, I mean, that's moving throughout the course of the night, the course of your observing session, because of the rotation of the Earth. So say we've got the Earth with its axis of rotation. We're sitting at some point on the Earth. So the Earth is rotating that way around this axis of rotation, but we're looking at upwards and sideways in our azimuth. So we're doing a rotation which is going that way, and we're doing another one which is going that way. So we've now got two axes of rotation on our mount for the telescope in altitude and azimuth, neither of which are the same as the rotational axis about which the objects in the sky are moving. So if we want to track an object through the sky, we need to move our telescope in two axes, in both altitude and azimuth, in order to sort of, you know, piecewise keep tracking the object that's just rotating in one axis in the sky. So you've got first problem there, we're having a track in two axes. But the other thing that's causing a problem with that, if you think about a field of view, so say this is what we're looking at through the eyepiece, and we can move it up and down and right and left. Now that's great, except the thing that we're looking at is rotating round. So we track around and we're keeping the telescope in the same orientation of what up and down and right and left is. Well, if this object has moved round to here, what was up on the object at that point straight up there is now going off to the side here. So the object's rotated in our field of view. So if you're then tracking an object for an extended period of time, it's then changing its orientation. It might be going from pointing upwards to pointing, okay, you'd have to be tracking it a long time for it to be pointing off to the side. But still, you get the point. You're getting a change in the orientation. So over the course of an exposure, if you're taking a photograph, say you're taking a photograph of a galaxy, you might spend half an hour tracking that object. You've then got a significant change in orientation of the object over the course of the photograph. And that's not very good because you're going to get blurring. So if you want to then have better tracking and better opportunity for doing photography, astrophotography, then an equatorial mount is going to be your go-to option. And before I go on to the equatorial mount slide, that's why I've got this first picture here, because you'll see with this picture here, this first one, it looks a bit like the fourth one we got over here, as in we've got a fork mount. But now you'll see that this is aligned way off to the side here. You know, our axis here, this is flat at the top of the tripod. Here, this has got this wedge in, which has angled it. And this is where they've added a wedge to turn an Altazimuth mount into an equatorial mount. As in now this axis here, this one which is going perpendicular to this flat bit, so what would have been our vertical axis here, this is now off to the side and aligned parallel to the axis of rotation of the Earth. So this is what is happening in equatorial mounts. So let's go to the equatorial mount slide and we can have a closer look at this. So you can take an Altazimuth mount, particularly a fork mount, and turn it into an equatorial. You can't really do that with Dobsonians. I mean, Dobsonians are much more, you know, they are what they are. They're cheap mounts for being able to support very large, cheap telescopes. But you see here, we've now got a different setup with our axes of rotation. So let's look at this picture on the left here. We've got one axis. Oh, I've drawn. Oh, yeah, we got one axis going up here. I thought I'd drawn the wrong line in for a second. Yep. So we've got one axis going there. And then we've got another one, which is going here. So again, they're perpendicular. But this one, this second one that I've drawn in here, if you rotate about that, that is, and this is how you want to set up the telescope, having that axis aligned with the axis of rotation of the Earth. So when we're tracking an object, we just need to rotate in that axis, not the other axis. So this is, the two ways this is going to rotate. Yeah, we've got that axis there, as I say, with this rotation, and then we got this one here. And the way we achieve this rotation is, you'll see in this case, you get these things called, if you haven't wired it up to a motor anyway, these things called slow motion controls. There's one of them here on a lot. These are sort of flexible little attachments you have to the axis of rotation, and you twiddle this knob round at the end. So if you twiddle this, it will rotate the telescope tube about this axis. And if there'll be another one, I think, oh, you can just about see it here, which would be on a shorter, it won't be on one of these long flexible tube things normally. It will be closer attached to the axis of rotation there, and that will move it in the axis in the same manner as the rotating Earth. So we've got those two options there. So this is attached to what's called the declination, and this one is attached to what's called right ascension. So we've got the two different axes of rotation have got different names now, right ascension and declination. So this is more of a latitude and longitude approach to dividing up the night sky. So we've included now, you know, axis of rotation and equator. So now we've got right ascension, which is going to be rotating through longitude, through east-west, and we've got the declination, which is going to be rotating through latitude north-south. So it's much more like what you see in an atlas. I mean, in terms of the actual tube, you'll see this is much the same as what we had on the Dobsonian mount. You know, it's still a Newtonian reflector. We've still got primary mirror down here, secondary mirror up, behind here. It's going to be, this is where the eyepiece is put. So the secondary mirror is going to be mounted up here. So we're going down the tube, hitting the primary mirror, back up, hitting the secondary mirror, and then out the eyepiece here. So it's still a Newtonian reflector, it's just on a different mount. So the telescope's the same, the mount is different. We're now rotating about two different axes. So to set these up though, I mean, first of all, I've scribbled all over this picture, which is why I've included this second picture here of a equatorial mount. And these are German equatorial mounts. I mean, you've got this one's a bit more robust. You can see, well, if I hadn't scribbled all over the original picture, you can see this is a fairly intricate bit of metal work, which is putting all this together. It's more robust than the mount on the left. It's more robust and expensive than the Dobsonian mounts. So you can see this is going to require a lot more precision engineering than what could be a bit of chipboard cut into various forms for a Dobsonian mount. So these are more expensive, and then you have to set them up in a particular way, because you want to, in order to get your axis aligned with the rotation of the Earth, that is going to depend on your local latitude. So when you get your telescope and you set up the mount for a first time, then you'll see these things down here. These will allow you to change essentially take this axis and swing it backwards and forwards so that it is what your local latitude is. There'll be a little reader on here somewhere where it'll be able to tell you, set it roughly to whatever you are, I don't know, 50 degrees north or whatever it might be. That gets it close. You'll also see that there's a cap here, and there'll be another one here at the other end, which allows you to look through the center of this axis here. So if you then take your telescope out for your first night observing, and you can look through there and you can try and align the tripod to the pole star. So you'll have various ways of getting this, close or, to a certain or lesser degree, depending on how accurate you need it to be. If you're just doing a casual observing session, then you can get it close. It doesn't need to be crazily close. But yeah, if you're wanting to do long exposure photos, then you might want to have a more precise way of setting it up. But it allows you to align your mount a little bit more accurately than you could do otherwise. So that means you've got that angle in place. So you're then rotating with the Earth. Then you've got these bits here, which are your counterweights, because you don't want to have a tension in your mount. So when you put the telescope on here, you can then take all of the locking devices. So all of these little things are little locking devices that lock your axes of rotation in place. So you can undo all of those and then get your telescope balanced. So you move these counterweights up and down this metal rod here so that your telescope is balanced perfectly. So that the weight on this side of your mount is counteracting the weight of the telescope on the other side. And then you've got your mount set up. So there's more you need to do with these equatorial mounts in order to get them usable, set up. They're more expensive to manufacture. So you've got a lot of stuff going on here, but they are very, very useful. And if you've got a telescope like this, you might have a 4, 5, 6 inch, maybe even bigger. But even as a beginner, if you're getting one of your first reflecting telescopes, you might have, say, I don't know, a 6-inch aperture on there. You can put one of those on a German equatorial mount. You can do some fairly impressive astrophotography. You can stick a camera of some variety in here instead of an eyepiece, and then you can track it across the sky, either using the slow motion control manually, just twiddling the knob on the bright ascension there, or you can actually attach that to a motor drive that will just move at a constant speed that matches the speed of the rotation of the Earth. So yeah, you've got a lot of options there for doing some good astrophotography. So there's pros and cons for both of these sort of mounts. I mean, one thing actually that does come up, I was saying how easy it is to point a Dobsonian or some other out as mount object in the sky. Equatorial mounts, you can end up getting yourself into some weird positions with the rotations of the telescopes. And you can also get the case, particularly if you're looking at things that are very high up in the sky, where the telescope tube will then bash against the tripod leg. You've got it that the tripod's set up like so. The telescope's now very pointed at something very high up, and you can get collisions down here. And then people sometimes get stuck as well. What on earth am I meant to do now with this telescope? How do I keep on tracking? And you get this thing called the meridian flip, where you essentially rotate the telescope 180 degrees in right ascension, and then you reset the declination to find the object again. And then so there can be two different ways of getting your telescope to point at a particular object. So yeah, it can be interesting being able to set up the equatorial mount to actually direct the telescope at the object that you're interested in. It can take a little bit of getting used to, but it doesn't take that long. And then next thing you know, you're doing meridian flips without even thinking about it, and getting back to tracking your object without any great issues. But yeah, sometimes when you're starting out, you can feel a bit like a contortionist trying to work all of the different permutations. So anyway, that's a brief overview of the basics of telescope mounts. And if you get into observing, do not underestimate the importance of a good mount, depending on what it is you're trying to achieve. Certainly if you're wanting to do some photography, you want something which is going to be sturdy. But yeah, in that case, I mean, you don't think you have to have an equatorial mount in order to do good astrophotography. I mean, you get field rotation if you've got a fork mount, but you'll see some telescopes. You might get a catadioptric telescope, so one of these short tube Schmidt-Cassegrain telescopes. So these sort of things that are quite popular, these chunky ones on fork mounts. You can take perfectly good photographs of the moon and planets and things like that, short exposure stuff, where you don't have to worry about field rotation particularly. So don't think you have to have an equatorial mount in order to do astrophotography. But it's worth knowing the pros and cons of all of these different ways of setting up your telescope. There you go. Now I'll leave that there for now. I think that's enough to get people to have the general idea.